Hello, everybody. I'm going to wait just for a little while for everybody to get here. We'll wait until officially 10 o'clock to get started. But I can write on the board where we're kind of at. Let me get this centered as best I can. So where we were at last time is we were in section 26, and today we're going to start with a corollary. This will be 26.7. But like I said, I'll wait just one more minute to get everybody in here. Feel free to say hi on the chat or something just so I can see that actually people are here. Great, Ethan. Nice to sort of see you. So hopefully we will actually be back in our classroom on Friday. That is what the reports are saying, is that we should have power and lemons on Friday and we'll be back in class. But for today, I thought I'd just jump on the board in my office and we'll just teach from here. So let's see, it looks like a few more have arrived. Feel free to say hi to everybody in the chat so everybody knows who's here, and we'll get started in just like one more minute. All right, who else is in here? Constance is here. Very good. All right, I'm going to go ahead and get started. Oh, good. Some other people. Grant's here. Katie's here. Tim's maybe watching with Ethan. Sounds good. Okay, perfect. Let's get started. So we're still in section 26, and we've been learning about the mean value theorem and things like the mean value theorem. Today we're going to start with a corollary, so let me write it down. So the corollary is let f and g be continuous on AB and differentiable on AB. Suppose that g prime of x is equal to f prime of x for all x's in AB. Then there exists a constant, let's call it capital C, such that f of x is equal to g of x plus c on the closed interval from A to B. Okay. So first of all, let's just talk for a second about what this corollary is saying. And basically what it's saying is, let's say that you have two functions and they have the exact same derivative. So you have the g prime of x and f prime of x are exactly the same thing, okay, over some interval. Then they can not be the same function, but they only differ by a constant. So you can't have like two funky functions that both have the same derivative, but they're totally different functions, but they have the same derivative. If two functions have the same derivative, then they're basically the same function except for a constant. Okay, let's prove that that is the case. So proof. Let's let h of x be equal to f of x minus g of x. Okay, so we've got h of x is equal to f of x minus g of x. And now what we could do is we could find h prime of x. So each of these are differentiable functions. So I can easily find the derivative h prime of x. So we have that h prime of x is f prime of x minus g prime of x. But we know that f prime of x and g prime of x are the same function. So f prime of x and g minus g prime of x is 0. So here we have a function, call it h of x, whose derivative is identically 0. And we learned about this last time. One of our theorems said that if we have a function whose derivative is identically 0, then that function itself must be constant. So we can use that, and we can say that so that means that h of x is equal to a constant. Let's see, that's by Theorem 26.6. Let's see, 26.6. So Theorem 26.6 tells us that if we have a derivative that's always 0, the function must be constant. But that means that f of x minus g of x is a constant. So f of x minus g of x is some constant c, or we have that f of x is equal to g of x plus c. And that's what we wanted to show, is that the function f of x must be just g of x plus some constant. And that's the proof. So that one's pretty easy to prove if you construct this new function h. And that shows us that if two functions have the same derivative, then those are basically the same functions other than possibly just the constant. Okay, let's write down a couple definitions. So definition, a function f is strictly increasing on an interval I if x1 being less than x2 implies that f of x1 is less than f of x2. Okay, so what it means to be strictly increasing on an interval is take any 2 points in that interval, you choose. One of them is going to be the small one of them is going to be the large one. And if that implies that the functional value of the first one is less than the functional value of the second one, then it's increasing. If you wanted to look at this on a graph, take an x1, take an x2. If f of x1 then is less than f of x2, but that's true for any 2 points you take, then it must be kind of making its way upward. So it's increasing. Similarly, we could talk about a function being strictly decreasing. So definition, a function f is strictly decreasing on an interval I if x1 less than x2 implies that f of x1 is bigger than f of x2. So this is what it means to be strictly decreasing. So if you take any 2 points, one's the small one, call it x1, one's the large one, call it x2, If f of x1 is always bigger than f of x2, then this thing must be kind of making its way downward. And so we say that the function is strictly decreasing. Now, we're not going to use this as much right now, but we're adding this word strictly. And strictly basically means it doesn't stay flat for a while. So a function could kind of be going down, level out for a while, and then keep going down. That function, we would typically just say it's decreasing, but it's not strictly decreasing, because notice this is a hard greater than or a hard less than. It's not less than or equal to. And so strictly decreasing means it's always going down, strictly increasing, always going up. Okay. So now that we know what we're talking about when we talk about strictly increasing or strictly decreasing, we could write down another theorem. So this is theorem 26.8. And it says, let f be a differentiable function on an interval I then two things. First, part A, if f prime of x is greater than 0 for all x inside our interval I, then f is strictly increasing on I, and B, if f prime of x is less than 0 for all x in I, then f is strictly decreasing on I. Okay, so this gives us another way of thinking about being strictly increasing, or if you'd like to think of it from left to right going up, or strictly decreasing, or from left to right going down. Another way of thinking about that is saying, oh, well, if the derivative is positive everywhere, it's strictly increasing. If the derivative is negative everywhere, it's strictly decreasing. And this isn't like shocking news if you've taken some calculus, right? You know that positive derivatives mean increasing, negative derivatives mean decreasing. And that's exactly what this theorem is telling us, is how to recognize when something is increasing or decreasing. So let's prove this. The proof of part A and part B are almost exactly the same. So I'm just going to prove part A, and B is very, very simple. Okay, proof. And this is proof of A, I guess I should say. Proof of part A. So let's suppose that f prime of x is greater than 0 for all x in some interval I. Okay. Then, if x1 and x2 are both in I, and x1 is less than x2. So we just choose 2 points in I. One of them has to be the small one, right? And so we'll just call the small one x1. So x1 is less than x2. Then f of x2 minus f of x1 is equal to f prime of c times x2 minus x1 by the mean value theorem for some value c that lives in x1 to x2. Okay, so f is a differentiable function on the interval, meaning differentiability implies continuity, so it's continuous on the interval. Take 2 points inside the interval, and this will give me that the mean value theorem holds. Well, the mean value theorem says that f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. I just multiplied both sides by x2 minus x1, and I get this result. Okay, so this is just true by the mean value theorem. Okay, so what do I know? I know something about the derivative at c. I know that the derivative of c, we said that it's always positive. So this value is positive, correct? But if this value is positive, what do we know about x2 minus x1? x2 is the bigger one. So x2 minus x1, that's positive. So this guy's positive, this guy's positive, positive times positive is positive. And so this value, f of x2 minus f of x1, that's positive. But if f of x2 minus f of x1 is a positive number, that means that f of x2 must be bigger than f of x1. So let's write this down. So since f prime of c is bigger than 0, and x2 minus x1 is also bigger than 0, that implies that f of x2 is bigger than f of x1. So, and that's true for all points x1 and x2 in the interval. So f is strictly increasing on pi. And of course, it's similar for part B. We're just going in the other direction where the derivative is always negative instead of the derivative being always positive, but it's the exact same argument, okay? I know it's harder to ask questions online, so I don't feel bad if you don't type out a really long question, but if you do have any questions, feel free to post them and I will check periodically to see if anybody's typed anything, and I'll answer your questions if I can. But this is our proof that if we have negative derivatives, it's going down. If we have positive derivatives on an interval, it is going up, or it is increasing. Okay, that brings us to another theorem. So this is Theorem 26.9. And this one is called the intermediate value theorem for derivatives. So we've heard of the intermediate value theorem. We study that one in calculus class. This one we don't study as much. This is the intermediate value theorem. Oops. So the intermediate value theorem for derivatives. Let me write it. So let f be differentiable on closed interval from A to B, and suppose that K is a number between f prime of A and f prime of B. Then there exists C in AB, the open interval, such that f prime of C equals K. All right, so this is very much like the intermediate value theorem. The intermediate value theorem says, let's say you have f of A and f of B, then the function must hit every functional value in between A and B if it's continuous and nice, right? This one says, let's say it's differentiable as well, and say that K is a number between the derivative at A and the derivative of B. Then this is saying that it has to hit all the derivative values between f prime of A and f prime of B in between f prime of A and f prime of B. So if you pick any K in between, there's a C that hits that derivative value. Okay, so it's very similar to the intermediate value theorem. It's just for derivatives instead of for the original function. Okay, so let's prove this. Okay, so proof. So without loss of generality, let's assume that f prime of A is less than K is less than f prime of B. Now, what's the without loss of generality for? Well, it could be flip-flopped on these inequality signs. It could be greater than K, greater than. So right now we're just assuming that this has the little slope, this has the big slope. Okay, it doesn't have to. This could be the little slope and this could be the big slope, but it's the exact same argument. So for the purposes of our argument, we'll let this A be the little slope, B will have the big slope. Okay, and we choose some K in between those two. All right, so now we're going to define a new function. We're going to let g of x be equal to f of x minus K times x. Now, certainly we know that f of x is a nice differentiable function. K times x is just a constant times x. We know that's a differentiable function. In fact, we even know what its derivative is. It's negative K. So I'm just adding another differentiable function to f. So g, this new function, is a nice differentiable function, right? So that's good for us. Then g of x is differentiable on AB, and here's the important part, g prime of A is strictly less than 0, is strictly less than g prime of B. Now, do we buy this story? Let's see. Well, I know what? That this guy, what do we have here? So if we plug in A, what is the derivative of this function, by the way? I haven't even written it down. So real quick over here, let me write this down. G prime of x is equal to f prime of x minus k. So let's think for a second about G prime of A. G prime of A is f prime of A minus k. Well, f prime of A I know is less than k. Minus k is negative. So this guy's negative. Similarly, if I plug in B, G prime of B is f prime of B minus k. F prime of B is bigger than k. So this guy has to be positive. So I have I have a negative derivative here, and I have a positive derivative here. Okay. G is continuous on AB because differentiability implies continuity. So I know that G must also be continuous on AB. So by corollary, this is 22.3. G assumes its minimum value at some point C that's inside of AB. Okay, it assumes its maximum value too, but we only need one of them, so we're just going to take the minimum. So somewhere in between A and B, it could be at the endpoints, right? It could be at the endpoints that it assumes its minimum value, but it does assume a minimum value in there somewhere because it's continuous on a closed interval. Okay, so here's what I want to do. I'm going to claim that this value C is in the open interval AB. So I'm going to say that minimum value actually happens somewhere inside of the open interval, not at the endpoints. So I need to show that that's true. So the way that we're going to show that is let's look at G prime of B. Well, G prime of B, that's the derivative of G at B. That can be defined by the limit of a difference quotient. So let's write it that way. This is equal to the limit as x goes to B of G of x minus G of B over x minus B, which is positive y. So why is this thing positive? Well, didn't I say it was? Yeah, right here. I said G prime of B is greater than 0. So I know that this limit is bigger than 0. If it's bigger than 0, then it's bigger than 0 sort of everywhere around it in a small interval. And let me write that in a more definite way. So this is how we'd like to say this. So that means that G of x minus G of B over x minus B is greater than 0 for all x inside of some open interval U intersect with AB, where U is a deleted neighborhood of B. Now, we're only concerned inside of AB as well. So if you're inside of that deleted neighborhood and you're inside of AB, the only points that aren't B are to the left of B, right? So if we're only talking about points that are in this interval coming at B, so it's to the left of B, okay? Thus, for x's that are less than B, or to the left of B if you like, and x inside of u, we must have that g of x is less than g of b. Why? Well, come over here again, right here. We know that this thing's positive. X, if you're in that deleted neighborhood and you're in a B, X is to the left of B, so X is less than B. If X is less than B, this thing must be positive or negative. So B's bigger, so this bottom is negative, which means this also must be negative. And if this is negative, then this one must be smaller than this one. And that's what I said. This one is smaller than this one. Okay, so that means that there are places nearby B where g of x is smaller than g of b. In fact, everywhere very close to b, that's true. Okay, so g of b is not the minimum value of G on AB. So what I just showed is this is not the minimum on the interval. There's something smaller. I could do the exact same process and also show that G of A is not the minimum. Okay, so so it's similar for G of A. So if G of B is not the minimum and G of A is not the minimum, then somewhere in between A and B is the minimum. So C in AB is the minimum. Therefore, what do we know about the derivative values of minimum and maximums inside an open interval for a differentiable function? We proved last time that they must have derivative value 0. So what we know is that therefore, by theorem, 26.1 implies that G prime at that minimum value C must be 0. So we have that there is a C in between A and B where the derivative of G, which was this function, is 0. Okay, so G prime of C is equal to F prime of C minus K. And we know now that that's equal to 0. Therefore, we have that F prime of C must be equal to K for some C in AB. And that's what we wanted to show. Okay. So that's kind of cool. So not only do we know that if you have an f of A and an f of B and a nice continuous differentiable function, we're going to hit everything in between. In fact, in that case, you just need continuous. But if it's continuous and differentiable, then it also hits all of the derivative values between f prime of A and f prime of B. It'll hit all the derivatives in between. So that's the intermediate value theorem for derivatives. Okay, so there's just really one more thing I want to write down here. I'm not going to prove this theorem, but I do want to write it because it's interesting. And it can be helpful when getting certain derivatives done in calculus. So let me write it down. This is theorem 26.10. And it's called the inverse function theorem. And it says, suppose that f is differentiable on an interval capital I, and that the derivative f prime of x is not equal to 0 for all x's in the interval. So we have a function that is never 0. Okay, then f is injective f prime, I'm sorry, not f prime, but f inverse is differentiable on f of I, and finally that f's inverse prime at a point y is equal to 1 over f prime of x, where y is f of x. Okay, I'm not going to take the time right now to prove this one, but I did want to write it down because there's actually some really interesting applications of this theorem when it comes to like proving the derivatives of inverse trig functions and stuff like that. You can do those using this theorem. So what this is saying is if we have a function, it's nice and differentiable, and we know that its derivative is non-zero. Now, if it's nice and differentiable and its derivative was not like negative somewhere and it was positive somewhere, we know by our last theorem that it must cross through 0. So if it's never 0, it's either all positive or it's all negative. But if it's all positive or it's all negative, then it's either strictly increasing or it's strictly decreasing, which means what? If it's strictly increasing or decreasing, it must be injective. And I'll let you think about that for a second. If you think about it for a minute, that's fairly straightforward, that strictly increasing and strictly decreasing functions have to be injective functions. Then it says that the f inverse function is differentiable on f of I. That's interesting, and you can kind of think about that as a limit of a difference quotient argument. And then finally, you get that if you want to take the derivative of the inverse function at y, then that should be 1 over the derivative at x. And this can be very, very helpful when you're trying to derive inverse functions derivatives. Things that come to mind are like, how about logarithms and exponentials? If you can figure out one of them, then you should be able to derive the other. What about sine and like arc sine? If you find one, you should be able to find the other, and so on and so forth. So this is a very useful theorem. If you're interested in the proof is in the book. Okay, so that's the end of section 26. I will officially assign homework now on section 26. Any questions from anybody before I sort of sign off here? I'll wait just a minute. Yeah, okay, so somebody asked about the midterm. I don't have my syllabus right in front of me, but I think it's coming up soon, right? I think it was beginning of March, which is coming quite quickly. I need to look at the syllabus to be sure what I say on the syllabus, but I will talk about that on Friday in class. I'll be ready with an official date for the midterm. Okay, right now we've got it listed as 3-3, which is, let's see, 24th. Let's see, March 3rd is a Wednesday, so that would be a week from today. Yeah, I think that we'll plan on keeping it there on March 3rd. So I'll talk more on Friday about exactly what proofs need to be known for the midterm, but let's plan on March 3rd as of right now. All right. Thanks, everybody, for joining, and I will see all of you on Friday. Hopefully, we'll be back in Lemons. Bye.